Hello everyone! Another video on NES Tetris, kind of a joined one to my other video. While creating the tool for planning out various moves in NES Tetris, I ended up diving very deeply into the code base, well, a little bit into the code base of how Tetris generates the next piece, how it figures out which the next one is going to be, and the goal behind that was so just that I could be absolutely certain of the maths behind the probabilities, so that when the tool was evaluating which option you should go with, you pick the right one, because if you treat all of them as being 1/7 chance, then you end up you could occasionally choose the wrong option based on what the probabilities say is going to come next. So I kind of wanted to make this video to run through, because I think the public knowledge about how the pieces are selected is slightly wrong. It's very close, but it's not quite the same thing. And actually, to kind of present some problems that I see right now. So yeah, in a simple enough world, we'd expect each piece happens 1/7 of the time. NES Tetris doesn't use the 12-bag randomizer that future Tetris games do. Yeah, so that would be very simple. However, we know that NES Tetris says that you are less likely to get the same piece that you just had, because then you just end up with, I think, what have been termed floods of pieces, where you have many in a row. So yeah, I think kind of the standard idea behind what people think the randomization is in NES Tetris is you roll an 8-sided die. So if it rolls, yeah, assuming that that's 1 up to 8, if it rolls between 1 and 7, then actually, let's not say it around that way. Let's first say it this other way. If it rolls 8, or if it rolls whatever the previous piece was, then we kind of do a re-roll. And so you would then roll a 7-sided die, and you take that result. So if it repeats the previous piece on that re-roll, then you take it. That's fine. And obviously, if you just roll the 8-sided die and it comes up 1 to 7, not repeating your previous roll, then just take that piece anyway. So this is the table that you would expect to get. To get the exact same piece as last time, you need to either roll this on your 8-sided die. You need to either roll an 8 or the same value as your last piece was. So that happens 2 out of 8 times, and then to get the same as the last piece, you're rolling a 7-sided die. You just need to get your exact piece. So that happens 2 in 56 times, and so the percentage comes out as 3.57. Any other piece, you have a 1/8 chance of just rolling that straight away. And then the other situation is, I think maybe this should be, yeah, there should be 2/8 and 1/7 here. It works out the same, but I just kind of typoed these, I believe. So the result of that comes out to 9 out of 56, so 16.07%. And hopefully, if we add all of these up, you've got 16.07 6 times, I would imagine, plus 3.57. Yep. So yeah, this is what you would get if everything worked perfectly, and this is what most people tend to think of. You have this bias against the piece you just had, and all the other pieces have equal chance. So you get a different piece around 4.5 times more than you get the same piece. So yeah, this doesn't actually work. When you actually look at the code, that's not what happens. It's very close, but it's not the same. So yeah, I linked here, and I will link in the description. There's an absolutely amazing analysis of the code of the game. I focus specifically on picking tetrominos, but this thing just goes through absolutely everything in the game. It's an amazing analysis of the whole thing. So I really recommend you kind of go and check it out. It looks into the memory addresses of the game, kind of tells you everything that's going to happen. Absolutely wonderful. So that was by Mike Birkin at meatfighter.com, it seems. I can't give enough credit for that because this is 90% of the work is right here. So yeah, here is the kind of idea behind what happens. Each piece has a spawn ID. So a T piece is stored at value 2. This is in hexadecimal, so base 16. J at 7, Z at 8. The O piece is stored at A, which in decimal is represented as 10. This would be represented as 11. E is 15, I think. And then I here is at, I think, 18. So basically, say that I had a T piece just now, then when we roll our kind of 8-sided die, if the value is 0, it would stay on the T piece, because it's basically, it will take your existing piece and then add on some number between 0 and 7. So if I had a T piece and I rolled a 0, I would remain on the T piece for that. If I had a T and rolled a 1, I would go to 3. So it can be a little confusing because, we actually have it now that 0 represents a T piece, the value 0 represents a T piece, 1 represents a J, 2 represents a Z, and so on. So this can be a little confusing. You don't need to know it too well. So this is happening. This is only in the reroll scenario. So say we've already done this this idea, roll an 8-sided die, and then roll an 8-sided die, and then you pick the pieces, and if you need to re-roll, then that's where we come into this scenario. So this only happens a quarter of the time. And so there is that idea behind you roll a 7-sided die and take whatever thing that is, but it doesn't actually roll a 7-sided die. The code in the game isn't really able to do that. It has to roll another 8-sided die. And that's why you get this dice roll, 8-sided die, and the answers come from 0 up to 7. And so what you actually tend to see is that when you roll a 0, you actually, because of the way that these kind of numbers work and what happens when you add extra bits on and take it modulo 7, you end up with this 4 and 4. And so what ends up happening is that in the reroll situation, there are 56 possibilities, and here's what the answer will come out to based on each of those possibilities. So you would expect to see each of them occur exactly 8 times, and that would be fine. But you don't. You see that the T appears 9, and so does the S. J, Z, and O all appear 8 times, and then the L and the I appear 7. So in this reroll scenario, based on the code, again, like you don't need to understand exactly the implementation of it. You can take me at my word, and I'll show some kind of code that generates this later. You end up getting fewer L's and I's and more T and S, and that's only in the reroll scenario. So when we actually look at the full scenario, so a quarter of the time you do the reroll, the other 3/4 of the time you don't, you end up with this frequency. And so instead of all of the pieces appearing the exact same amount of the time, you actually end up with these very slight differences. So the T and the S pieces appear most often, 14.73%, and L and I appear less often, 13.84. So again, Mike says this in the analysis, the I piece is less likely to come up than the other pieces, which we all feel at times, but there's actually statistical value behind that. So what it means is that every, I think is it 224? If we just add all these up, yeah, every 224 pieces, you actually get one I piece less than you should. And you'll get one T piece more than you should. This is, again, probabilistic. Like, this doesn't have to happen in a single game. It doesn't have to happen every 224 pieces. But it happens, statistically that often. So, this is just another slide. I wrote this kind of presentation up, but I figured I'd just talk through it and see where we get. So yeah, what I really wanted to know, especially for the Tetris planning tool that I was creating, if I know my last piece is a T, what do I know about the piece after that? So yeah, there's obviously the few answers that you can go through. Completely naive, where they're all equally likely. Nobody thinks that. The reroll answer, which most people think, which would basically just reasonably tell you, hey, it's probably not going to be another T piece, but it's going to be equally likely all the other ones. That's fine. But then when we kind of start looking into this code, we see these different frequencies, and we know that there's actually a slight difference. Now, this one really is such a small difference here, because you only end up getting like one more T piece than you normally would. You only get one fewer I and L piece than you normally would. So the difference is like 14.34% and 14.23%. So probably don't change your gameplay based on that. It's very small and it won't really make a difference. But there is a little bit more that we can do. Because of the way that the table works, you can actually, we were looking before at kind of the columns of the table. And when you start to look at the row, you actually see something a little interesting, which tells you, and this seems to have been known from a couple of people that I've spoken to, but I don't think it's known in the wider community. It turns out that there's actually a really big, what I would say, a very big difference in what you would expect to see. And so you actually can say, oh no, I'm more likely to see this next piece given the piece that I've already had. And we'll get into the numbers of it. And like I was saying, I'd say this is a big difference, but it's around kind of 3%, 4%. That, to most of us, to me especially, is not going to make any difference. I'm not a good enough player. My PB is about 600,000. But I think that when you kind of have to start thinking about this one, and you may be able to say something as simple as, well, I should be planning for an L piece rather than a J piece. And if you can make decisions based on that, even when it's these small percentages, then it actually can make a statistical difference as you play, as you put in the kind of many matches that people are going to have. If you're making these small decisions better, very slightly better than somebody else, it's going to add up. So yeah, as this slide says, it may sound far-fetched, but I have been really into professional poker as well. They make calculations like this based on, is this very slightly more profitable in a game theory sense? And I think it can apply in the same way. If you're applying very small probabilities to improve your strategy, then you have an edge over someone else. I think if you've seen videos over the past couple of years on how NES Tetris has changed, the skill ceiling is rising and rising and rising. So any small improvements that we can give are really going to help a bunch of the top players. For me, I still need to learn a lot more things than that. So let's look at this table. I know I said that the kind of indices confuse things a little bit, so I did change, the memory addresses into the pieces and these ones as well. Okay, so if we look at this column, I have a T piece right now. And so there's going to be an 8-sided die rolls, a random number between 0 and 7. And let's have a look at the pieces that I'm going to get. So if I have a T, I could get Z, O, S, L, I, T, J. And then it repeats. It comes back around. Z. That means that if I have a T piece, This again is in the reroll scenario, so this only happens a quarter of the time. The other 3/4 of the time, you still just have the initial roll. But in this situation, I'm twice as likely to get a Z as any of the other pieces in this reroll scenario, which is kind of crazy. And this isn't, I didn't see this anywhere. I ended up speaking to a guy on Reddit who it seems had done a bunch of the work on the initial mod for CTWC, or had some ideas on the CTWC mod to make sure that they get the same piece sequences. That guy's name is Kitaru, and he's been really, really helpful in just kind of explaining how this stuff works, what things are known. I thought I'd really uncovered something new, but it turns out other people knew about it already. So yeah, you can see a T is more likely to lead to a Z piece, a J is more likely to lead to a T piece, and a Z is more likely to lead to a J. So you actually, I think the most likely cycle that you end up in here is that a T goes to a Z goes to a J goes to a T, and in all likelihood, you would probably see that cycle a lot more often than you would see most other things. Other interesting ones on the O and S, they repeat on themselves. So an O is actually, in this reroll scenario, once you're in the reroll, you're more likely to see an O than you are anything else. Still, there's the bias against that generally, but that means that both O and S are more likely to repeat straight after each other. So you're more likely to get a string of O, O, O. And I feel like I've seen this. I've seen a lot of situations where there are strings of 3 of the same piece, maybe even 4 of the same piece. And now that I look back at it, I realize that in my mind, most of those are O ones, maybe because it's more noticeable, but O and S, it turns out, are statistically more likely to do that. An L goes to a T, and an I goes to an S. So yeah, I'll put this this PowerPoint up in case anybody wants to take a look through it. I have hopefully put all of the analysis down correctly. But yeah, so if you want to just have a guess in mind for this, know that a T goes to a Z, J to a T, Z to a J. O is more likely to produce another O, S is more likely to produce another S. They're still not the most likely pieces, but yeah, the L goes to a T and the I goes to an S. This is a useful table. This is actively useful. So let's take a look at the numbers on this. So in the first roll, each piece has a 1/8 chance of being chosen, and then if we're in the reroll, which happens if you roll an 8, so 1/8 of the time, or if you roll your previous piece, which happens another 1/8 of the time, then we can calculate the chances. And so this, I believe, is the kind of final calculation on what we need. So, for example, in a T piece, to get another T, that will still happen 1 in 32 times. It's exactly as it should. But then the J piece is the one that the T is more likely to lead to. So you actually end up with 6 out of 32, and all of the others are 5 out of 32. So when you have a T piece, or say that in the next box you can see a T, you can plan, if you assumed that it was going to be a J after that T in the next box, you're going to be slightly right slightly more often. 18.75% of the time you'd be right. Whereas if you guessed, any of the others, or assumed that they were going to be the same, you'd only be right 15.625%. And that is very small. It's three and a, yeah, I guess 3.5, 3.25% difference. No, sorry, just slightly over 3%. We'll go with that. But like I said, I think that these very small things add up. And then you can also see it on the ONS side. So that with that one, it's 15.625 every time, and the extra 1/32th chance that comes from this goes to itself. So normally you'll see a 3.125% chance of repeating, and with these ones you see a 6.25 which does make a difference. So yeah, I'd already spoken about that part. So yeah, like I said, this is the table to remember, and I think this is useful. I think people should consider starting to integrate this into their games. So all of this came when I was actually looking into this, trying to figure out how the piece generation worked. And when I realized that it was there, I didn't really believe it. And so I actually kind of coded up the yeah. So this is, I hacked this together. It's not very good given I hard coded all of these things. But basically in this situation, it's like, okay, let's run 10 million times 10 million and 1 because we only care about from one piece to the next one. So the very first piece doesn't count as one of those transitions. Yeah, some of this is boilerplate, but basically this is what the code does. Yeah, so this entire section is basically what I took from the code base of NES Tetris. I wrote it in JavaScript, and this generates the pieces exactly as NES Tetris would. The only difference being that I use the JavaScript randomization function. I'm making the assumption here that the NES Tetris random number generator is good enough, is pretty good random number generator, and I think that's a very reasonable assumption. And so my code does exactly the same logic as what it would do. And so if we go and if we run this RNG, I just called it rng.js because I am not original. And so I kind of put it out. We get a total of, I think, 10 million. And so what we see is the T appears 14.67% of the time, which we said it was slightly more. The J appears 14.29, Z 14.28, 14.28. The S is appearing slightly more often as well, which I believe is what we said, and then the L and the I appear slightly less often. So it's clear, like, that is what happens. They are not equally distributed pieces. There are very, very small changes. And so these inner ones basically say, in this situation, if I have an I piece and then I get a T piece, what's the chance of that? What's the probability out of all of my I's, which, there were 1.39 million I's, how many of them were followed by a T? What proportion of them were? And so you see in this 15.58, 15.6, 15.6, 15.6, 18.8. And we said in this, an I is most likely to go to an S. So I had already kind of worked through this logic, and then I coded this up and saw that it was accurate. So what about the O to the O? We would expect that to be right here. An O to an O would be 6.25%. So if we have a look, we actually see 6.21, which is pretty good, especially we've just done 10 million iterations. Like, there can always still be a bit of variance in that. So that's really cool. I find that really exciting. I think it's very different, and I think that even though it's a small change, it should actually be people should take note of that this can change strategy. You can plan very slightly, and if with my Tetris Planning app, which I've been showing off a little bit, you can actually say that there were two scenarios with an L and a J. Let me just check which one. Yeah, L is less likely to come and J is more likely to come. Say that you go, okay, well, I don't really mind which one of these it is. If I use the L in this situation, if I'm getting an L and it works out better, and a J and it works out about the same, then it doesn't really matter which one I do. But we know that an L is less likely to come. So if you're planning your stack with expecting a J to come slightly more often than an L, you're going to work out better off. So that means that it's really important to try and consider these in what you would consider equal scenarios. If there's one that's clearly better, probably you don't need to use this because they are very small percentage differences. But you can kind of make the plans in this way. So what did I have next? I had something else to show, I'm sure. Yes, that was it. This doesn't seem to apply in the CTWC same piece mod, which I think is very odd to me. So when I was kind of talking with Guitarro about this, I was kind of asking, I had transcribed, I can actually show here. So, no, sorry for the cut there, ended up showing some files that I wasn't intending to show, so I have to cut that out. What I did was actually go and manually transcribe from the finals of the 2019 CTWC. I also did both semifinals as well, and basically said game one starts with an O piece, T, O. Turns out you can get quite fast at doing this, and so I ended up watching it at like 1.5 times speed. When the transition hits, it gets very difficult to keep up. And so what I did was just transcribe all of these. I went to the finals, I did the semi-finals as well. And so with those, I felt like there was enough data that I could use in. So I did this CTWC 2019. I grab those and basically strip out any unnecessary parts and only consider the transitions from one piece to another within the game. I add them all up and then throw them into the same analysis that my RNG file does. It obviously doesn't generate any piece sequences, it just looks at what the patterns are. And so we can see that this was the RNG. We got, as expected, I pieces less than 14% of the time. And then when we do it with the compile list, actually this one still goes up to 14%, but it's lower than we would expect. This actually looks a little odd. Yeah. I've looked at these numbers a few times, but I'm trying to kind of figure things out a little bit. Yeah, actually, that's it, of course. The point that I'm trying to make is that CTWC mods don't seem to have this bias. So I's are appearing 14% of the time, L's 14.4, 14.2, the O's slightly less. This is not what you would expect from NES Tetris. Z's 14.4, like quite often 14.5, 14.2. So we're not getting the piece distribution bias. And then if we look at the transitions, one of the big ones was O to an O was happening around, I think, was it 3.5% of the time? Whereas now it's happening the very regular amount. So it turns out that what CTWC mod is doing is actually doing what people think. It's the roll an 8-sided die, and then if you need to re-roll, roll the 7-sided die and just pick whatever piece that is. It doesn't have any of these little quirks, the kind of bitwise quirks that I told you about. And that is very reasonable in the way that it's kind of implemented. The idea, was to make sure that people get the same pieces. But my contention is that we should not be changing the probabilities of the game. We should be playing exactly NES Tetris, quirks and all, the kind of weird stuff that people may not have realized. And so I'm of the thought that we need to change the mod that's used so that it, or the kind of piece sequences that it's able to choose, so that it represents exactly correct NES Tetris as opposed to some glorified idea of it. The very kind of small one in this is that you would expect to see an eyepiece less than 14% of the time, and then in CTWC you're going to see it 1/7 of the time, right? Which is, statistically you'll see it 14.285% of the time. You're getting more line pieces at CTWC than you should in practice. Maybe that feels like it makes it a little bit easier. I think a very naive approach to scoring the difficulty of the game is how many line pieces do you have. But we shouldn't be changing the probabilities of that. We should be conforming to exactly what the game is. Otherwise, we're playing a very slightly different game. So I just kind of wanted to make a video on that. First of all, I think that the probability differences are really interesting. People should consider them when planning their strategy. But there's the other part where I think that the CTWC mod that's used needs to change to more accurately represent the probabilities of the actual game. And that's all I've got to say on this one. Thank you very much for watching through. I know it's been a fairly long one. I will put all links to any of this code. I'll put it up in a repo on GitHub. Anybody can play with it if they want. I'll upload the presentation somewhere if anybody wants to check through it. If there are any mistakes in any of this, please let me know. I'm very happy to correct them. And thank you very much.